Okay, let's talk about integration. Integration we're going to start out by defining as the area under a curve, and to do that we're going to need to talk about partitions. Let me kind of draw a picture first and we'll talk about what's going on with this picture. So say we have this function f of x and we want to find this area between a and b under the curve. Okay, so what we do is we typically partition this up into equal-sized rectangles, and we estimate the area under the curve for each of these widths and take that average, and as we get more and more rectangles the integral gets closer and closer to the actual area under the curve. Okay, that's fine and that's a good way to do things, but we need to be a little bit more careful when we're doing the actual analysis of this. So let's get this function again, and we'll start at A and end at B, and I'm going to call a partition. So a partition, it's just going to be some collection of points between A and B. They don't have to be equally spaced. Maybe there's a whole bunch in there. Maybe I've got kind of a big space in this area, but that would be a partition, and there's going to be a finite number of points. I'll call this first one x1, A is going to be x0, this is x2, x3, x4, and so on. How many do I have here? 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and B is going to be x15, here's x14, and so on. And this partition is going to give me an approximation for the area under the curve. It's going to give me two approximations actually. It's going to give me an upper approximation and a lower approximation. Okay, so let's zoom in on this. So my upper approximation, let's do that in dark green. In this interval here between x0 and x1, in this first interval, there's a maximum value that the function takes. That's going to be m0, capital M0. And there's also a minimum value that the function takes, and that's like right here. That's going to be little m0, and that gives me two different rectangles. It gives me a bigger rectangle than the area and a smaller rectangle than the area, and they're going to give us a way to calculate the upper area and the lower area. And we do that again for this interval. There's the lower one, that's at m1, and there's an upper one, and that looks like it's here, and that's at capital M1, and so on. And so I got capital M2, capital M3, capital M4, capital M5, 6, 7, 8, 9, 10. Then in here it's sort of in the middle of the interval. We've got 11 and so on. And those are the upper ones. That's M2, M3, M4, and so on. And I've got lower ones too. I've got the lower guy. Oops, don't want to copy. I've got the lower guy here. There, lower guy, lower guy. Lower guy, lower guy, lower guy, lower guy. And here, where's the lower? Lower's right there. And then if I scale over, That green line is definitely not the upper guy. Looks like the lower guy is there, lower guy is there, and lower guy is there. Upper guys, I've got another upper there, and upper looks like it's about there for both, for at least this part, and then for this part it's in there somewhere. So I got the area under the purple rectangles, which is the lower integral, and I've got the area under the green rectangles, which would be the upper integral. So let's actually put some definitions together for these things, and then we're going to see how they work together to talk about integration. So, some definitions. A partition of the interval AB is a finite number of points xi from I equals 1 to n, where a equals x0, so I equals 0 to n. A equals x0, which is strictly less than x1, which is strictly less than x2, and so on, strictly less than xn minus 1, strictly less than xn, and xn is equal to b. Okay, so it's finite, and it's sort of they're a string of numbers that increase from a to b. Okay. Given, now we're going to do definitions some more, or notation maybe. For a partition P equal to xi from 0 to n, mi we're going to call the supremum for a partition P and a function f. Mi is going to be the supremum of f of x, and that supremum is going to run between x is in the interval from xi to xi plus 1, and little mi is going to be the infimum of the f values running over the x values between xi and xi plus 1. Okay, so these aren't left-hand endpoints or right-hand endpoints, they're the maximums inside the rectangles and the minimums inside the rectangles. Well, supremums and infimums, the maximums and minimums might not exist depending on what our function f looks like. Okay. L of P comma F. So this is going to be the lower integral. So what I'm going to do is I'm going to add up the size of those rectangles. It's going to be the lower ones. So it's going to be mi from I equals 0 to n minus 1. And then what I'm going to have to multiply by is the width, that's the height of the rectangle, the height of the lower rectangle. I have x I plus 1 minus xi. Okay, so that's the first rectangle, that's the width. This guy would be the width of the ith rectangle, and this would be the lower height, or the minimum value in that width. This is the lower integral of the function on the partition. Okay. And I have an upper integral. I've got u of p comma f, and that's going to be very similar. I'm going to use capital MI, and this is going to run from xi plus 1 minus xi. I'm going to take the height of the bigger rectangle times the width of the rectangle and add those up, and this is the upper integral of f on p. Okay. So that's just some notation. I need to do a little bit more with partitions, and then we're going to prove a few things about these partitions and these upper integrals and lower integrals, and see that they're kind of monotonic in how big the partition is. If I add more points to the partition, the lower integrals are increasing, the upper integrals are decreasing. A refinement, or adding more points to the partition, makes these get closer to the actual areas and closer to each other if the function is integrable. So I guess this is another definition. Given a partition P, if there is another partition, say Q, with P being a subset of Q, right? P is a set of points between A and B, Q is a set of points between A and B, then Q is called a refinement of P. Given two partitions, say P1 and P2, P star equal to P1 union P2 is their common refinement. So they are both refinements of P star because they're both subsets of P star, and there's a common refinement there. And now that we've got this notation, we can prove a small theorem. Let F map A, B into R, and P be a partition if P star is a refinement of P, then the following hold. 1, L of P comma F and L of P star comma F are comparable. And which one's bigger? Well, I've taken more points, so I've got a bigger partition. That means that my minimum values don't have as much weight as they did before. I'll draw a picture in a second. And here we've got the upper and the upper, and how they work is the maximum values don't have as much weight as they did before. So let's just draw a quick picture, and I think I'll leave that as a proof for you, but here's the picture. Okay, so let's call this f of x, and here's our first partition. Here's A, here's B. Let's take 3 points. So I've got 4 points, I guess. x0, x1, x2, and x3. So if the green is just P, and I've got a refinement, we'll throw in another point here, and maybe a point here, and this is going to be a refinement. So x0 is still A. Now this is x1, this is x2, this is x3, x4, and this is x5. So I've got 2 more points. Let's see why the lower integral of f on P gets bigger with the refinement. Okay, where's the minimum value in this first integral? Well, it's right there. So that's part of the refined lower integral. This is part of the refined lower integral. Just on this piece, the stuff that has been added to the lower integral in the refinement is this little extra box up here. Okay, like I was saying, this minimum weighted value here doesn't have as much weight as it did before because the interval that it works on isn't as big as it was before. I have a bigger lower value on this other part of the interval. Same here. Here's this point was added to the partition. What it would have been that, but what it is now is I've added this extra stuff to the lower integral. So the lower integral gets bigger when you add more points to the refinement, and similarly the upper integral gets smaller when you add more points to the refinement. Let's go with this one. So the upper integral used to be that over the whole thing. What I've taken away now is, well, the upper integral there, I've taken away this pink rectangle from the upper integral, and over here the upper integral used to be there, but now I've taken away that because my new upper integral is that and that. So the solid pink boxes have been taken away from the upper integrals due to the refinement. So that's what happens with these. And that's going to allow us to have sort of a monotonic sequence. We're going to put bounds on upper integrals and lower integrals, and when the upper integral, if I take the upper integrals and take the supremum of all of them over all partitions, then I have that's kind of a bound on how big the actual integral can be. Yeah, we'll see that next time.